All right, welcome everybody to a new challenge from the time complexity chapter to make sure that we really master and have understood it. So I have the function print numbers, right, which has one argument n, and yeah, this time it only prints numbers. So let's see how it works, right? First of all, I initialize I with the argument n, and as long as I is greater than 0, I make a for loop here in which I take each number from 1 to I and I print it. And then after the for loop finishes execution, I, of course, divide my value by 2 and I take the floor, right? So again, this function is floor. For example, if, of course, I could be even, and if it's even, everything is fine, right? The floor of 10 divided by 2 is 5. But the problem is when I is odd, the floor of 11 divided by 2 is also 5, right? So this is 5.5, and we take the floor, which is the integer part, which is 5. Awesome. So, yeah, let's first, as always, what do? We take a small example, we see how it works, we see how many operations we do, what's the values of I and J, and what do we print in order to then really understand and come up with the time complexity, right? So let's take a simple example. I don't know, I'm going to take n equals 8. What happens for n equals 8? When n equals 8, the first value of I is of course 8, right? So we start off with I equals 8. And then what happens? As long as I is greater than 0, cool. What do? We enter the while loop, right? So I entered the while loop the first time. And what do? This for loop, which says that I'm going to take each and every value from 1 to I, so from 1 to 8, right? J is going to take each and every value, and I'm going to just print J. Okay, so J is going to be 1, 2, 3, ... 8. And the values that I'm going to print are 1, 2, 3, ... 8, right? Awesome. Now, this for loop finishes execution. After it does, what I'm going to do is that I'm going to divide I by 2. And I'm going to take, the floor of that. But don't worry, I is even, so I became 4. Cool. Now, what's going to happen? Again, 4 is greater than 0, so I enter one more time the for loop. J starts with 1, and it's going to take each and every value in the range 1, 4, right? So J equals 1, 2, 3, and 4. And I'm going to print, of course, 1, 2, 3, and 4. Okay, cool. So here I have printed 8 values. Now I only print 4 values. Okay, let's see what happens next. After the for loop finishes execution, of course, my next value of I will be 2. So what happens with I equals 2? Well, when I equals 2, again, same spiel. We take each and every value in the range 1, 2, right? So J will be firstly 1, and then it's going to take the value 2. And then, of course, we have the last step in which I is equal to, let's actually clear this because the values that we output are definitely here, right? So I gets halved one more time, greater than 0. J gets the value only 1. One more time, right? After the for loop becomes 0. And yeah, that's the first bad value. And we exit the algorithm, right? So let's see what happens. I think it's pretty clear, right? So we have obviously 2 nested loops. We have the while and we have the for, which is for J, right? So what we are going to do first is analyze how many iterations the inner loop performs, right? And you can see, even on this example, you can see that the number of iterations is actually dependent on I, right? Because when I is 8, we take each and every value from 1 to 8. That's a total of 8 values. Here, when I is 4, that's a total of 4 values. So 4 iterations. 2 values here and 1 value here, right? So yeah, this is anyways obvious. You don't need to take an example because you can see very clear that J takes each and every value in the range 1i, right? So how many distinct values are there? Obviously I values, right? So this for loop will always perform I iterations, right? When I is n iterations, n divided by 2, n divided by 2 iterations, right? And so on and so forth. Yeah, the printing is constant. We don't care about it. This is also constant. We don't care about it. In conclusion, this piece of code So accepting this while loop, right? If we ignore the constants and all that stuff, we can say that it does I operations, right? So for each value of I, I'm going to add to my total number of iterations or operations the value of I, right? Which is exactly what happened here in my example, right? For I equals 8, I've done 8 iterations. I equals 4, I've done 4 iterations. 2, 2, and 1, 1. So what I'm going to do in order to find out for n equals 8 what is the total number of iterations my algorithm does is, of course, add all of this together, right? For each value of I, add how many iterations this piece of code performs for that value, right? So I get an 8 plus a 4 plus a 2 plus a 1. Cool. Now, of course, we need to think in terms of the general case, right? We don't know the value of n. It could be anything. So we need to see what are the values that I takes for a general n, right? The first value, obviously, is n, right? Because it is initialized with n. So I equals n first. We enter this while loop. And what we do here is n iterations, right? So I perform n iterations for I equals n. Now, after this piece of code finishes execution, notice that I is going to be half the value it was, right? So on the next step, on the next iteration of the outer loop, I enter with I equals n divided by 2. And I perform again n divided by 2 iterations. So the next one is n divided by 2, right? I should theoretically write floor of n divided by 2, but let's just write n divided by 2. That's okay. We'll know that it is floor there, right? Cool. Now, after this piece of code finished execution, of course, my I is also half the value it was. So now I'm going to enter the while loop again with n divided by 4, right? So the next one is n divided by 4. Again, I became half, n divided by 8. I perform again n divided by 8, and so on and so forth, until the last value of I, after it gets halved and halved and halved, is eventually going to be 1. So I enter, I do one iteration, then this 1 becomes 0, and when I try to enter the while loop, I won't because it's not valid anymore. So the total number of iterations can be expressed by this sum. Let's take a look here for n equals 8. Was I right? n, 8. n divided by 2, 4. n divided by 4, 2. And yeah, the last term of the sum is 1, right? So this is the total number of iterations. But the thing is that I can't express a time complexity using a sum, right? I can't say that the time complexity of this algorithm is n plus n divided by 2 plus n divided by 4 and so on and so forth. No. What we need to do in order to express the time complexity is actually find a simple upper bound for this sum, right? So an expression which depends on n, that we know for sure that the value of this sum won't ever exceed the value of that expression. And one thing we can do with this sum is, of course, notice that we have a common factor, right? N appears everywhere in those terms. So I can say that this sum actually here is n multiplied by 1 plus 1 divided by 2 plus 1 divided by 4 plus, and so on and so forth, until, of course, I get 1 divided by n, right? Cool. Now, what I want to tell you, and I don't expect for you to know this or maybe notice this, it's cool. I'm going to explain it to you. What I want to tell you is that this sum inside the parentheses is actually less than or equal to 2. Okay? Actually, I think it's less. It's strictly less. Yeah, it's strictly less than 2 to be specific. All right. So I'm going to tell you why is that. But before I do, because I know this sum is less than 2, I definitely know that this expression is less than 2 crossed n. So this is exactly what I wanted to achieve. I wanted to find an upper bound which is simple for this sum. If this sum is less than 2 crossed n, then I can say without a doubt that the total time complexity of this algorithm is big O of n, right? The total number of iterations, operations, whatever, that this algorithm does is always less than 2 crossed n. So big O of n is the right way to express the time complexity. Now, how will I prove that this sum is always less than 2? Well, we have two ways of doing that. The first one, which I'm not going to approach here, is that this series, 1 divided by 2, 1 divided by 4, 1 divided by n eventually, is a geometrical progression, right? So each term is actually the previous term multiplied by the same thing, right? So you take the first term multiplied by 1 divided by 2. Multiply this by 1 divided by 2, you get the next one. Multiply this by 1 divided by 2, you get the next one, and so on and so forth, right? And there is a formula for the sum of geometrical progressions. But I don't want to do that here. It's not intuitive. It's math, and trust me, you don't need it, right? So the other way of doing that and proving this is a more simple approach. This sum, 1 plus 1 divided by 2, again, 1 divided by 2, plus 1 divided by 4, plus plus 1 divided by n, is less than 2. For this to happen, let's subtract 1 in each of these terms, right? For this to happen, then what I need to do, or what needs to happen, is that 1 divided by 2 plus 1 divided by 4 plus plus 1 divided by n. So I subtracted 1 from this sum, has to be 2 minus 1, which is 1, has to be less than 1. Now for this to happen, let's also subtract again the first term of this sum. For this to happen, what needs to happen is that 1 divided by 4 plus 1 divided by 8 plus plus 1 divided by n. So I subtracted 1 divided by 2 from this sum, has to be less than 1 minus 1 divided by 2, 1 divided by 2. Now, in order for this to happen, guess what? What should happen? Let's subtract 1 divided by 4. 1 divided by 8 plus 1 divided by 16 plus plus 1 divided by n has to be less than 1 divided by 2 minus 1 divided by 4. This is 1 divided by 4, right? And so on and so forth until eventually we're gonna obtain that 1 divided by n, right, should be less than 1 divided by, and I think it's n divided by 2, something like that, right? So notice here that when the first term of the sum was 1, the value here on the right of the sign was 2. When this is 1 divided by 2, this was 1. When this was 1 divided by 4, this was 1 divided by 2, right? So the value here was always equal to double the first term of my sum, right? And each time removing the first term of the sum, I will eventually, in the end, get only the term 1 divided by n, only the last one. I'll be left with this one here, and the value here is going to be double it, so 1 divided by n divided by 2, or in other words, 2 divided by n. Stuff like that, right? Which is going to happen, right? So, yeah, there are two ways of doing that. I don't care how you do it. I just want you to understand and to really know why the time complexity of the algorithm is big O of n and not exactly prove mathematically these types of things, right? So yeah, that's it. And I'll see you on the next one. Bye. GG.